I'm going to talk about is why, oh why, are we talking about this and doing this? Because that is the part that usually stumps people. And so on the document that we looked at, it sums this up, but so that everybody is clear, the reason that we are even discussing this is because your answer cannot be more precise than the least precise number you used in a calculation. And so we're discussing how accurate and how precise measurements are, and the fact that you cannot calculate something that is more accurate or more precise than what you started with. And so I'll give you an example here just to illustrate what I'm talking about. Earlier I mentioned to you that on a standard ruler there are centimeter markings, etc., and then there are millimeter markings. I obviously drew my millimeter markings very accurately because they're all evenly spaced out. But when you are measuring something with a ruler, how precise can you possibly be? You cannot tell me how many micrometers you measured to the third or fourth decimal because you can't see that far. So on a ruler, what it explains on the handout I gave to you is that the most precise you can be is the half of a millimeter. Because you could actually see 2 millimeter markings and estimate that you were in between them. That's as precise as you could get. You could not tell me, for example, that you measured, let's say I measured something that was this long. You could not tell me that that was 53745 millimeters. There's no way you could tell me all of those decimal places because you don't have a tool to measure them. And so the reason we're talking about this is because of basically how many decimals you can give when you are measuring something. Now, it's not just the number of decimals, but that's usually an easy way to explain it. The most precise I could get with a ruler is just 26.5 millimeters. I couldn't be any more precise than that because there are not enough markings on the ruler for me to get any more detailed. And what we're trying to say is, if that's the measurement that you're starting with, and then I ask you to calculate something with it, your answer can't be any more precise than what you started with. That is the purpose. That is the reason that we are talking about this, because your answer cannot be more precise than the numbers you started a calculation with. So I'll just pause here for you to do. What I asked you to do was to summarize the rules for, first, significant digits. And so I'm going to show you what I would say are the rules for significant digits. A significant digit, by definition, are digits that you got from a properly taken measurement. Now, if I provide you with a question to answer on a piece of paper, we will always assume that we took the measurement properly, unless the question I'm asking you is, did this person take this measurement properly? Otherwise, you can assume that yes, the measurement was done properly. Now, the rules for significant digits tell you first to count all the digits from 1 to 9 plus zeros that are in between and following other digits. So what does that actually mean? I'll show you some numbers. The handout shows you some numbers as well, but I'll show you some numbers to illustrate that. Let's say that I have this number, 5,075. In the number 5,075, if I wanted to count how many significant digits there are, I count all of the numbers from 1 to 9 plus zeros in between and following another digit. So that means there are 4 significant digits in that number. All 4 of the digits count. Now I'm going to compare that to a number like this. In the number 0.507, there are 4 digits, but not all 4 of them are significant. This illustrates the second point. Do not count zeros in front of a value. So you can count a 0 as significant if another number comes before it. But you don't count a 0 if it's the first digit. So in my second example, we don't count what we call leading zeros. So this is called a leading 0. The zeros here would be called trailing zeros. If a 0 comes before all the other digits, it does not count as significant. So in this number, there are only 3 significant digits. The 0 in between the 5 and the 7 still counts because it is a trailing 0. It came after another number. The 0 at the beginning does not count because it's only there to set the decimal place. It tells us where the measurement started, but it's not actually adding any precision to the answer. Now there's another point in the handout about logarithmic numbers like pH, and since we are not going to deal really specifically with pH, like we're not going to calculate it, I'm not going to talk about that one really specifically here because we're not going to calculate with it. So I'm going to jump to the last one and talk about exact numbers. An exact number is something that is defined like a constant or something that I get from counting. So an exact number is not uncertain, and it has an infinite number of significant digits. I'm going to show you something. This little sideways 8 is the symbol for infinity. And so I would sometimes use that symbol when I'm making a question, let's say on a test, and I ask you how many significant digits does this number have. That little symbol there means infinity. So I will give you some examples of numbers that are exact. First, we have numbers that are defined or numbers that are constant. So for example, pi is a constant. The value of pi is 3.14159, blah, 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 blah. It keeps going and going and going. It has an infinite number of significant digits. It's a defined constant value. Something like Avogadro's number. That is a defined constant. It has unlimited significant digits. Something like that a kilogram equals 1,000 grams. When we're doing a unit conversion, we would never take away significant digits. So a unit conversion like that has unlimited significant digits. 1 kilogram exactly with unlimited significant digits is exactly equal to 1,000 grams with unlimited significant digits. The other numbers that have infinite significant digits are ones that you get from counting. So if I looked around the room today and I saw that there were 24 people, 25 including me, that number has infinite significant digits. It's not like there are 25.1 people or 24.9 people. There are exactly 25 people. So it could be a person, it could be an object, but if you are counting something, not measuring it, but counting how many of something there are, that number would have unlimited significant digits. Now that is how you sum up the rules for counting the numbers of significant digits. The other part of this page, maybe I'll just make a new slide here so we have space. The other part of this page was talking about performing mathematical operations. Because we are going to calculate things, that's kind of the reason that we're using significant digits, we need to know how to decide how many significant digits our answer will have. So if you look at the section called Rules for Performing Mathematical Operations, it tells you first about adding and subtracting, then about multiplying and dividing, and then the third point is more than one. And what we'll see is that we would follow the same basic steps for the more than one math operation as we would for multiplying and dividing. So there's really just two scenarios. If all you are doing is adding and subtracting, so you are adding and subtracting only, there are no other math operations happening, no multiplying, no dividing, this is the rule you'll follow. You'll see that you will rarely use this rule because most of the time we will be multiplying or dividing something. It's only once in a while that we'll use this rule. This tells us that your answer should have as many decimal places as the number with the fewest places to start. So what does that mean? It means, for example, if I wanted to add 15.15179 and 5.2, and I needed to know how to round my answer off, I would say to myself, hey, this number has 1 decimal place. This number has 5 decimal places. I'm going to pick the smaller number of decimal places, so that would be the one with 1, and that's what I'll report in my answer. So my answer would be 20.4, because I would round up because the number that comes after it is a 5. So this only applies if all you are doing is adding or subtracting. If at any point you are going to multiply or divide, or you are going to do more than one operation, this is where you need to know how many significant digits you have. So when you are multiplying or dividing or doing more than one operation, you count significant digits and use the lowest number in your answer. So, for example, if I was to divide 20.000 by 5, 20.000 has 5 significant digits. The 2 and all of the zeros that come after it are all significant. The 5 has 1 significant digit, so that's the smaller number. So when I report my answer would just be 4. No 4.0, just 4, because that's 1 digit. So what I'd like to ask you to do, so that you can practice these skills, is to look at the last page of the handout that I gave you. On the last page of the handout, there's a box that says Skill Practice Using Significant Digits. There are 3 questions in it that are all just little math calculations. In fact, the first question isn't even a calculation. It's simply asking you how many significant digits there are. Then 2 and 3 are asking you to do those little math calculations and give your answer with the correct number of significant digits. So this is a little piece of homework I would like for you to do.